A single cathedral could consume an entire forest before the first stone was laid. The soaring spires and massive walls we admire today were not shaped by ambition alone. They were carved from a hidden economy of forests, metals, and fuel. These three resources formed a tight feedback loop that set hard limits on what medieval builders could achieve. Why did some grand plans succeed while others were abandoned? And what happens when a society runs out of the very materials that power its greatest dreams? By the end of this exploration, you will see those landmarks not just as monuments to faith or power, but as the outcome of a fragile, living calculation between nature and human will. Have we ever truly understood the invisible scaffolding that holds up our own world? Between the 11th and 15th centuries, Europe embarked on an unprecedented building frenzy. Cathedrals reached for the heavens with vaulted stone ceilings and skeletal flying buttresses, while castles grew into sprawling fortresses of thick walls and towering keeps. Monasteries and abbeys multiplied across the landscape, each complex a small city of cloisters, dormitories, and workshops. The scale of this ambition is hard to grasp today. A single Gothic cathedral could require over 1,000 wagon loads of stone for just one phase of construction. Timber was consumed by the tens of thousands of trees, also for the immense roof frames that spanned vast naves. Iron was needed by the ton for reinforcing walls, forging hinges, and binding massive doors, while lead was essential for roofing and gutters, often taken from distant mines or even melted down from older buildings. The logistics alone were staggering: quarrying, felling, transporting, and lifting these materials across rough roads and waterways, often over years or decades. Entire regions were transformed as forests were cleared and quarries were carved into hillsides. And yet, for all this furious activity, the resources were not infinite. The question soon became unavoidable: what natural and technological constraints could possibly reign in such ambition? The answer lay hidden in the very forests, metal deposits, and fuel supplies that made these projects possible, and the limits would surprise even the most determined builders. Wood was the lifeblood of the medieval world. Every plank, every beam, every frame that held up a cathedral or a castle began as a living tree, and the scale of that hunger is almost impossible to imagine today. A single large cathedral project might consume the timber from 1,000 acres of forest, not just for the finished structure, but for the temporary scaffolding that rose and fell as masons worked their way upward, for the immense roof trusses that spanned the nave, and for the formwork that supported stone arches before the keystones locked them into place. And that was only one building. Multiply that by hundreds of abbeys, thousands of churches, entire fleets of ships, and the constant demand for fuel, and you begin to see a picture of a society that ran on wood the way ours runs on oil. Because wood was not just lumber, it was also the raw material for charcoal, the dominant fuel for smelting iron and firing glass. Forests were the original energy infrastructure, the hidden power grid that made everything else possible. Every nail, every hinge, every lead window came from the heat of a charcoal fire, and that fire was originally a tree. The medieval economy was a vast engine burning sunlight stored in wood, and the forests were the fuel tank. But that tank had a limit, and when it ran dry, the ambitions of builders would be forced to change in ways they never expected. The link between forests and iron was direct and unforgiving. To turn raw iron ore into usable metal, medieval smiths relied on a process called bloomery smelting. They would build a small clay furnace, fill it with layers of charcoal and crushed ore, and then light it. A bellows driven by hand or by water power forced air into the fire, raising the temperature just high enough to separate the iron from the rock. but the heat was never enough to fully melt the iron. Instead, the metal collected as a spongy, glowing mass at the bottom of the furnace, a bloom which had to be pulled out and hammered repeatedly to squeeze away the impurities and compact the iron into a solid bar. This method was terribly inefficient. A huge portion of the iron remained trapped in the slag, the waste material, and was lost. For every ton of usable iron that finally emerged from the smith's hammer, the furnace had consumed an enormous quantity of charcoal. And charcoal was not a simple commodity. To make it, woodsmen first felled trees, then stacked the wood in carefully constructed mounds covered with earth, and burned it slowly in a low-oxygen environment. The process took days or weeks, and it took roughly 200 acres of woodland to produce enough charcoal to yield just a single ton of iron. Think about that. 200 acres of forest stripped and burned for a material that would become a few dozen iron bars. Now multiply that by the tons of iron needed for a major cathedral. Iron was used for the reinforcing rods that tied stone walls together, for the hinges on massive oak doors, for the grills that protected windows, and for the tools that masons used day after day. Every nail, every axe head, every chisel had to be forged from that same finite supply. The health of the surrounding forests directly dictated how much iron could be produced. If the woodland was depleted, the bloomeries fell silent. This was not a problem that could be solved by importing iron from far away, because even imported iron had to be produced somewhere, and that somewhere faced the same charcoal constraint. The true upper limit on medieval metal was not the ore in the ground, it was the trees standing above it. In this way, the forests were not just the fuel for the fire. They were the invisible hand that reached into every forge, every workshop, and every building site, deciding how much iron was available for the great ambition of the age. The most impressive cathedrals were often built in regions where forests were thickest, because only there could the charcoal supply keep pace with the demand for metal. And as those forests shrank, the iron supply shrank with them, quietly setting boundaries that even the most determined builders could not cross. That shrinking of the forests was not a slow, distant problem. By the 13th century, it had become a pressing reality across Europe. Regions that once seemed blanketed in endless woodland began to feel the strain, especially near growing cities, busy mining districts, and industrial centers where the demand for timber and charcoal reached a fever pitch. The medieval appetite for wood was so immense that it began to outstrip the land's ability to replenish itself. A single charcoal pit might require an acre of forest every few years, and with hundreds of pits feeding iron furnaces, glassworks, and lime kilns, the forest edge retreated further and further from human settlements. Wood that once could be gathered within a day's walk now required journeys that took days or even weeks. The cost of lumber and charcoal climbed steadily, and that cost was felt directly in the budgets of ambitious building projects. Timber shortages became a common headache for cathedral chapters and castle lords. They had to search farther afield for suitable trees, paying higher prices for transport over rough roads or down rivers. Sometimes they were forced to reuse older timber, salvaging beams from dismantled structures or buying up second-hand wood from abandoned buildings. In extreme cases, builders had to compromise on the scale of their original designs, using thinner beams or reducing the height of roof frames because they simply could not find or afford enough large, straight trees. The grand vision of a soaring spire or a vast hall began to bump up against a hard physical limit. The forest could not grow back fast enough. A mature oak might take a century to reach the size needed for a major beam, but the medieval economy was consuming those trees in a matter of decades. The tension between continuous demand and painfully slow regrowth forced a difficult choice. Either you scaled back your ambitions, or you scoured the map for new sources of wood, often at great expense and risk. This scarcity also reshaped everyday life. In many towns, local ordinances began to regulate wood cutting, imposing fines for taking timber from common lands. Forests that had once been open for fuel and building material became guarded resources, reserved for the nobility or the church. Ordinary people felt the pinch when winter came and firewood grew scarce, or when their houses needed repairs and a new beam cost more than a month's wages. The crisis was not sudden, but it was relentless, and it forced a slow, grinding adjustment in how society thought about the natural world. The forests had seemed endless, but they were not. And as the trees vanished, the ambitions of builders had to learn a new kind of humility, one that was measured in the slow, patient rhythm of regrowth that no amount of human will could hurry. And yet, even when the forests could supply enough charcoal, the metal itself remained stubbornly difficult to win from the earth. Medieval mining was a world away from the industrial operations we might picture today. Most mines were small, shallow, and worked by hand. A typical iron mine might be little more than a trench dug along an outcropping of ore, or a narrow tunnel driven into a hillside with pick and hammer. Miners followed veins of ore by candlelight, often in cramped spaces where a single collapse could bury weeks of work. The deeper they went, the harder it became. Groundwater seeped into the tunnels, and without efficient pumps, a mine could flood and become unusable. Ventilation was a constant challenge. The air grew stale, and the fumes from candles and torches made breathing difficult at depth. Reaching a rich seam of ore required not only labor but also luck, and even then, the ore itself was rarely pure. It had to be crushed, sorted, and washed before it could be smelted, and each step lost material. A ton of ore might yield only a fraction of a ton of usable metal. The entire process was slow, unpredictable, and expensive. For a cathedral project that needed iron for reinforcing rods or lead for roofing, the supply was never guaranteed. Lead and tin mines faced similar problems. In Cornwall and Devon, tin miners dug deep into granite hillsides, following narrow lodes that twisted unpredictably. The ore had to be hauled to the surface in baskets, then crushed with heavy wooden stamps powered by water wheels. The resulting powder was washed in running water to separate the heavier tin particles from the waste rock. Even then, the smelting process was inefficient. Early furnaces lost a significant portion of the metal to slag, and the quality of the final product varied widely from one batch to the next. A bell cast from impure metal might crack on its first ringing. A lead roof sheet could develop weak spots if the lead contained too many impurities. Builders had to accept this inconsistency, ordering extra material to account for flaws, and often relying on trusted local smiths who knew the idiosyncrasies of their own furnaces. Copper was even more difficult. It required higher temperatures and careful control of the smelting process, and pure copper was soft. For applications that needed hardness, like bells or tools, it was usually alloyed with tin to make bronze. But that meant coordinating two separate mining and smelting operations, each with its own uncertainties. The result was that medieval metal was never a standardized commodity. It was a local, variable, and often fragile resource. The structural uses of metal in grand buildings were therefore limited. Iron tie rods could hold stone walls together only if the iron was strong enough and free of cracks. Anchor points for flying buttresses had to be forged from the best available stock, and even then, builders sometimes reinforced them with extra stonework to compensate for weak metal. Bells, which required precise tuning and immense forces, were cast in special foundries where the recipe for bronze was guarded as a trade secret. The entire system of medieval metalworking was a triumph of human ingenuity, but it was also a constant negotiation with the imperfections of nature. Every bar of iron, every sheet of lead, every bronze bell carried within it the memory of the dark mine, the smoky furnace, and the patient hands that had shaped it. And those hands knew better than anyone that the limits were not just in the forests or the ore bodies. They were in the fire itself and in the stubborn, beautiful inconsistency of the raw earth. The fire that shaped the metal had its own hidden chemistry, and that chemistry was not forgiving. Medieval smiths learned through centuries of trial that not all fuels were equal. Wood burned too quickly and left too much ash. Peat, that dense, dark earth cut from bogs, smoldered slowly but never reached the temperatures needed to melt iron ore properly. It was fine for warming a home or cooking a stew, but for a bloomery furnace it was almost useless. The heat it produced was not intense enough to separate iron from rock, and what little metal did form was weak and full of impurities. Early coal, which lay in seams just beneath the soil in many parts of Europe, seemed like a promising alternative at first. It burned hot, much hotter than wood, and it was abundant. But coal carried a hidden flaw that ruined the iron. When coal burned, it released sulfur compounds that soaked into the glowing metal. Sulfur made the iron brittle, prone to cracking under stress. A sword forged with coal-fired iron might shatter on the battlefield. A cathedral tie rod made from the same metal could snap without warning, bringing down walls and vaults. The damage was invisible until it was too late, so builders and smiths stuck with charcoal despite its enormous cost in land and labor. Charcoal burned clean. It produced a steady, intense heat without sulfur or other contaminants. The metal that emerged from a charcoal-fired furnace was pure, strong, and reliable. The trade-off was brutal. A single ton of iron required dozens of acres of forest, but that iron would hold a cathedral together for centuries. In regions where forests thinned and charcoal grew scarce, smiths tried desperate experiments. They mixed peat with charcoal to stretch supplies, but the resulting metal was inconsistent. They attempted to wash coal to remove sulfur, but early methods were crude and only partially effective. Some builders resorted to using more stone and less iron, reducing their dependence on smelted metal altogether. But that meant thicker walls and lower ceilings, a direct compromise on the grand designs architects dreamed of. The choice of fuel was not a minor detail. It was the invisible hand that determined whether a vault could rise 60 feet or 100, whether a bell could ring clear or crack on its first note. Every beam of timber, every bar of iron, every sheet of lead carried within it the signature of the fire that made it, and that fire was never simply wood or peat or coal. It was a negotiation between human ambition and the stubborn rules of chemistry. The forests bore the scars of this negotiation, but so did the finished buildings, standing for centuries as monuments not only to faith and power, but to the slow, careful mastery of heat and fuel that made them possible. The cost of moving these materials was often greater than the cost of producing them, and that simple arithmetic reshaped the geography of ambition. A forest might stand thick with timber, and a quarry might hold stone enough for 100 cathedrals, but if no river ran nearby and the roads were nothing more than muddy tracks worn through the fields, then the resource might as well have been on another continent. Overland transport in the medieval era was brutally inefficient. A single ox cart could carry perhaps a ton of stone or a few large beams, but it moved at a walking pace, and the animals needed food and rest. Roads were often impassable in rain, rutted from heavy use, and vulnerable to banditry. The cost of hiring the cart, the oxen, and the drivers could easily triple the price of the stone by the time it reached the building site. For a cathedral that needed thousands of tons of material, the haulage bill alone could swallow the budget of a small kingdom. Builders had to make hard choices. They might source stone from a quarry only a few miles away, even if the quality was inferior, rather than bring in better stone from a distant river. They might use local timber for scaffolding and reserve the imported oak for the most critical roof beams. Every mile added to the supply chain was a tax on the project, and that tax was paid in time, money, and often in the sacrifice of the original design. Rivers and the sea offered a cheaper alternative. A boat could carry the load of dozens of carts, and water provided a smooth, continuous route that did not wear out animals or break axles. But rivers were not everywhere. They froze in winter, flooded in spring, and sometimes ran too shallow for fully laden barges. Coastal shipping required sheltered harbors and favorable winds, and the ships themselves could be lost to storms. The network of navigable waterways was a scattered and seasonal thing. A site like the great cathedral at Rheims sat far from any major river, forcing its builders to rely almost entirely on ox carts for its immense stone blocks. The cost and effort of that transport became a hidden limit, one that silently dictated which projects could rise and which would remain as plans on parchment. The great monuments that still stand today are not just works of art and faith. They are also monuments to logistics, to the careful calculation of how far a resource could travel before the price of movement exceeded the value of the material itself. The same rivers that carried stone also turned the wheels that transformed medieval industry. Wherever a stream ran fast enough, engineers built mills that captured its energy and put it to work. Water wheels drove bellows that forced a steadier, more powerful blast of air into bloomery furnaces, raising temperatures and improving the yield of iron from each load of ore. They powered trip hammers that pounded red-hot blooms into bars with a relentless rhythm no human arm could match. They turned saw blades that ripped through timber far faster than any pit saw, slicing beams for roofs and scaffolding with mechanical precision. These innovations did not just save sweat, they saved fuel. A water-driven bellows could maintain a consistent draft hour after hour, burning charcoal more completely and extracting more metal from the same weight of ore. Trip hammers shaped iron more quickly, reducing the number of reheating cycles and the charcoal each cycle consumed. Sawmills turned logs into lumber with less waste, so fewer trees needed to be felled for the same number of beams. It seemed like a perfect solution: harness the endless power of flowing water to stretch the shrinking forest further. But every solution carried its own hidden cost. As water-powered systems grew more sophisticated, a new invention emerged in the late Middle Ages that promised to revolutionize iron production: the blast furnace. This was a taller, more efficient furnace that used water-powered bellows to force air through a much hotter fire. Instead of producing a spongy bloom, the blast furnace could actually melt the iron, allowing it to flow out as liquid metal that could be cast directly into mold. The resulting cast iron was harder and more uniform than anything produced by a bloomery. It could be used for cannon, for heavy tools, for structural components that demanded strength and consistency. But there was a catch. The blast furnace needed to run continuously, day and night, for weeks or months at a time. Once lit, it could not be allowed to cool without ruining the furnace lining and wasting the charge inside. That meant an endless appetite for charcoal fed into the top of the furnace in a steady stream. A single blast furnace could consume an entire forest in a season. The same invention that freed iron from the limits of bloomery inefficiency now tied it more tightly than ever to the health of the woodlands. The water wheel turned faster, the bellows blew harder, and the furnace roared hotter, but the fuel came from the same source as always: the living trees. And as forests receded, the blast furnace became a hungry engine that drove their retreat even faster. Medieval engineers had found a way to amplify human labor, but in doing so, they had also amplified the demand on the natural world. The trade-off was stark. Every leap in technical skill came with an equal leap in ecological pressure. The rivers might flow endlessly, but the forests could not keep pace. And so the great machines, for all their ingenuity, could only postpone the reckoning, not avoid it. Salisbury Cathedral rose in just 38 years, a remarkably short span for the 13th century. That speed alone makes it a compelling case study, because most cathedrals took generations, sometimes centuries, to complete. The difference lay not in the ambition of its builders, but in the quiet cooperation of the landscape around them. Salisbury was built on an entirely new site, chosen for its flat, open ground and its proximity to the rivers Avon and Frome. Those rivers became the cathedral's lifeline. Blocks of limestone from the Chilmark quarries, about 12 miles away, were loaded onto barges and floated almost to the building site. Timber came from the dense woodlands that still covered much of the region, oak and beech that provided beams for the immense roof frame and scaffolding for the masons. Lead for the roof sheets was mined from the Mendip Hills, just a few days' journey to the west, and iron for reinforcing rods and hinges was smelted in local bloomeries fed by the same forests. The materials were all within reach, and the water routes made their transport efficient. Yet for all this abundance, the cathedral that emerged was not the largest or the tallest of its age. Its spire is famous, added later and reaching over 400 feet, but the main body of the building is modest in scale compared to the soaring naves of Amiens or Beauvais. Why settle for less when the resources seemed plentiful? The answer offers a quiet lesson in sustainable ambition. The builders at Salisbury worked within the limits of what their immediate region could supply without turning into a drain on distant forests and mines. They had good access to timber, but not unlimited access. They had iron and lead, but every ton of metal cost acres of woodland. The project was ambitious enough to be a landmark, but not so enormous that it would strip the surrounding countryside bare. In that balance, the cathedral stands as a reminder that even the greatest works of human hands are shaped not only by vision and skill, but by the quiet voice of the land, a voice that says this far and no further. The success of Salisbury was not a triumph of ignoring limits, but of understanding them. No material embodied those limits more clearly than iron. Walk into a medieval cathedral today, and you might notice the stone seems to float, held together by nothing but gravity and faith. But look closer, iron is there, hidden in plain sight. Iron rods run through the masonry, tying walls together and preventing them from bulging outward under the weight of the vault above. Iron cramps, short bars bent at both ends, were set into stone blocks to lock them in place, especially around windows and doorways where the walls were thinnest. The intricate stone tracery that fills Gothic windows, those delicate patterns of circles and arches, often had iron bars threaded through them to hold the glass and distribute the wind load. Huge iron hinges supported the massive oak doors, and iron bands wrapped around the timber to keep the heavy planks from splitting. Bells, the voice of the cathedral, were cast in bronze, but they hung from iron frames and were rung by iron mechanisms. Yet for all these uses, the iron itself was remarkably scarce. A modern skyscraper is built around a skeleton of steel beams, a continuous frame that carries the entire load. The medieval builder had no such luxury. Iron was far too expensive and too difficult to produce in large quantities. A single ton of iron required hundreds of acres of forest to make the charcoal for smelting, and the entire process could take months. Every bar of iron was a significant investment, and it was used with extreme care. The iron in a cathedral was not a structural skeleton. It was more like stitching, a series of small, targeted reinforcements that held critical points together. The walls themselves carried nearly all the weight, and the iron was there only to prevent them from slowly spreading apart under the constant pressure of the stone vault above. This fundamental scarcity shaped the entire form of the building. Because iron could not be used to tie walls tightly together at every level, the walls had to be thick and heavy on their own. The vaulted ceiling pushed outward, and without a continuous iron frame to resist that thrust, the stone walls had to be massive enough to absorb it. This is why early Gothic cathedrals have such thick lower walls, and why the windows had to remain relatively small. Too much glass and too little stone meant a weak wall, one that iron alone could not save. The great innovation that allowed windows to grow larger was not iron reinforcement, at least not directly. It was the flying buttress, that graceful arch of stone that leaps from the outer wall to a thick pier, carried the outward thrust of the vault down to the ground, freeing the wall between buttresses from the burden of holding the roof up. That thin wall could then be filled with glass. The buttress was a structural solution born directly from the limits of iron. Builders could not simply bolt the walls together with steel ties, so they invented a stone frame that did the same work. The height of the vault was also constrained. A higher vault pushes outward with greater force, and without iron ties to resist that force, the walls had to be proportionally thicker, or the buttresses had to be more numerous and more massive. The builders of Beauvais pushed this logic to its breaking point. They designed a vault that reached 157 feet, the highest in Europe. But the choir collapsed twice, and the nave was never completed. The iron available to them was not enough to hold those soaring walls together, and the stone buttresses they built could not quite handle the load. The building stands today, but only as a fragment, a permanent reminder that the ambition of the architect must always answer to the stubborn truth of the material. Iron was not the servant of medieval architecture. It was a limiting factor, a whispered boundary that every designer had to listen to. The most beautiful cathedrals are not the ones that ignored that boundary. They are the ones that understood it and turned constraint into an art form. Glass demanded its own invisible forest of fuel. The stained glass windows that flood cathedral interiors with color are often celebrated as the crowning achievement of medieval art, but behind every radiant panel lay a furnace that burned for days on end. Making glass was not a delicate craft of gentle flames. It was a brutal, fuel-hungry process that consumed wood by the cartload. The basic ingredients were simple: silica from sand or crushed quartz, mixed with potash made from burned beech or fern, and sometimes a little lime to stabilize the mixture. But turning those raw materials into a workable sheet of glass required temperatures approaching 1100 degrees Celsius, and sustaining that heat for hours demanded an enormous and continuous supply of charcoal. A single furnace could burn through an entire wagon load of fuel in a single firing, and that was only the first step. Coloring the glass added another layer of fuel cost. To achieve deep blues, craftsmen added cobalt oxide. For rich reds, they used copper or gold. Each color required precise temperature control and sometimes multiple firings as the glass was reheated and worked into shape. A window with many small pieces in varied colors demanded far more furnace time than a simple panel of clear glass. The finished pieces were then assembled on a wooden frame, with lead strips holding them together, and the whole window was installed in a stone opening that had to be carefully prepared to support its weight and resist wind pressure. Every stage of this process, from the initial melt to the final lead work, drew on the same finite resource, the surrounding woodland. In regions where forests had already been depleted by charcoal burning for iron smelting and by timber harvesting for construction, the additional demand for glass fuel could push the local landscape past its breaking point. Some cathedral chapters found themselves forced to choose between fewer windows or smaller windows, simply because the wood to fire the glass furnaces was no longer available within a reasonable distance. The density of glazing in a cathedral is therefore not just an aesthetic decision, it is a fossil of the local fuel economy. A building like the Sainte-Chapelle in Paris, with its vast expanses of stained glass that seemed to dissolve the walls into light, was possible only because the city sat at the heart of a region that still had access to substantial woodlands and well-established charcoal supply chains. In contrast, cathedrals built in more deforested areas, or in regions where iron production had already claimed the best timber, often have noticeably smaller windows or fewer colored panels. The glass was simply too expensive in fuel terms to produce in quantity. Even the transportation of finished glass panels added to the cost because they were fragile and had to be packed carefully, adding weight and bulk to already strained supply routes. The beauty that streams through those windows is not just a gift of artistic skill. It is a testament to the willingness of medieval society to burn through its forests in pursuit of light. Every pane of cobalt blue or ruby red carries within it the shadow of the trees that fed the furnace, and the quiet arithmetic of a world that was always counting the cost of its own brilliance. The same logic of hidden fuel costs applied to every metal that held a cathedral together. Lead sheathed the roofs, lined the gutters, and sealed the joints of stone spires, but its weight in wood was just as heavy as any iron bar. The lead came from deep mines in the Peak District and the Mendip Hills, where miners followed veins of galena, the natural ore of lead, through narrow tunnels lit only by candles. Once brought to the surface, the ore was crushed, washed, and smelted in furnaces that burned charcoal by the ton. A single sheet of lead for a cathedral roof might require the wood from several acres of forest, and a full roof could consume hundreds of acres before the last sheet was laid. The demand for lead was so intense that it drove a slow but relentless deforestation of the hillsides around the major mining districts. Woods that had stood for centuries were cut and burned to feed the smelters, and the landscape never quite recovered. The scars of that hunger are still visible today in the bare, rolling slopes of the Mendips, where the trees never grew back as thickly as before. Builders faced a direct trade-off between the pitch of their roof and the quantity of lead required. A steep roof shed rain and snow quickly, but it covered a much larger surface area, demanding far more lead. A low pitch roof used less lead, but it needed more careful construction to prevent leaks and could collect water in heavy storms. Some architects compromised with a moderate slope, calculating the cost of lead against the cost of timber for the roof frame. Others, like the builders of the Great Spire at Salisbury, chose a steep pitch and accepted the immense lead bill because the visual impact of that soaring silhouette was worth the price in forest. The choice was never purely aesthetic. It was an economic calculation etched into every inch of the roof line. Copper and tin followed a similar story. Bronze, the alloy of copper and tin, was the material of choice for bells and statues because it rang clearly and could be cast into complex shapes. But copper smelting required even higher temperatures than lead, and tin had to be brought from distant mines in Cornwall, far from most building sites. The combined fuel cost for a single large bell could equal the charcoal needed to smelt a year's worth of iron for the same cathedral. Every bronze bell that called the faithful to prayer was a monument to the forests that had burned to cast it. And as those forests shrank, the number of bells in a tower often had to be reduced, or smaller ones were cast to save fuel. The great peals we admire today were not just products of artistry. They were the result of a quiet contest between human ambition and the patience of the woodlands. The metal that covered the roofs and rang from the towers was never just metal. It was sunlight captured by trees, distilled into charcoal, and then transformed into the voice of a civilization. Royal forest laws did not simply protect trees for the king's hunting pleasure. They quietly shaped the entire geography of medieval ambition. When a monarch declared a forest royal, it meant that no one could fell timber, graze livestock, or collect firewood without explicit permission. This was not just a matter of privilege. It was a way of rationing a resource that had become too precious to leave unguarded. In England, the Forest Charter of 1217 codified these rules, placing vast tracts of woodland under strict supervision. Violators faced heavy fines, and the boundaries of the royal forests were surveyed by wardens who kept detailed records of every oak and beech. But the law did not apply everywhere. Outside the royal forests, the land belonged to local lords, abbots, or bishops, and they too had to manage their timber with care. A monastery might own a woodlot that supplied fuel for its kitchens, timber for repairs and charcoal for its smithy. But if the abbot sold too many beams to a cathedral project, the community could face a cold winter. Timber rights became a form of currency in the medieval economy. A lord could grant a tenant the right to take a certain number of trees for building, or to gather fallen branches for firewood, and these rights were recorded in charters that could be bought, sold, or inherited. The system was complex, but it reflected a fundamental truth. Wood was too valuable to be left unregulated. Charcoal burners formed their own guilds in many regions because their craft required deep knowledge of the forest and careful stewardship of the resource. A charcoal burner knew which trees made the best charcoal, how to stack a mound for even burning, and when to let a woodlot rest for a decade to regenerate. These guilds set rules about how often a forest could be harvested, and they policed their own members to prevent overcutting. In the Weald of southeastern England, a dense woodland region that became a major center of iron production, the charcoal burners worked hand in hand with the ironmasters. The landscape was a patchwork of coppice trees cut on a cycle of 15 to 20 years and stands of older timber reserved for structural beams. The iron industry there thrived for centuries because the fuel supply was managed with an eye toward the long term. Further east, in the Alps, the region of Styria developed a different model. Its rich iron ore deposits and abundant forests allowed bloomeries and later blast furnaces to operate on a scale that supplied much of Central Europe. But even there, the limits were felt. By the 14th century, Styrian ironmasters had to import charcoal from neighboring valleys because their own woodlands could not keep pace with demand. The cost of fuel became a factor in the price of every bar of iron, and that cost rippled outward to every building project that depended on Styrian metal. The cost of resources directly affected who could afford to build and what they could build. A wealthy patron, a king, a bishop from a rich diocese, or a powerful abbot could pay the premium for imported timber, iron, or lead. They could draw on forests from distant estates or buy charcoal from regions where wood was still plentiful. A cathedral like Notre Dame in Paris, backed by the crown and the wealthy bishopric, could afford to bring in stone from multiple quarries, timber from the vast forests of the Isle de France, and lead from mines in the massive Central. The project proceeded with a steady flow of materials, even when local supplies ran short. But many ambitious projects were not so fortunate. A lesser cathedral in a remote diocese, or a castle built by a baron with modest lands, might have to pause construction for years while the surrounding forests regrew. Some buildings were downsized mid-project, their naves shortened or towers left unfinished, because the cost of fuel for smelting iron or making glass had become prohibitive. The abbey church at Vézelay was never completed to its original plan, and historians have suggested that the depletion of local woodlands for charcoal played a role in that abandonment. The distribution of monumental buildings across Europe is not random. The densest clusters of great cathedrals and large castles appear in regions with ample water transport and rich forests, like the valleys of the Seine and the Rhine. In areas where wood was scarce, such as the limestone plateaus of southern France or the deforested hills of Tuscany, monumental architecture tended to be smaller, more compact, and built with less iron and glass. The pattern tells a story that is not about faith or ambition alone, but about the quiet economics of trees and charcoal. The patrons who succeeded were those who understood the limits of their landscape or who had the wealth to reach beyond them. And those who failed left behind the fragments that still puzzle us today, unfinished towers and empty niches that whisper of a resource that simply ran out. By the early 14th century, the great building projects of medieval Europe had pushed against a wall they could not see. Every forest that fed a charcoal pit, every mine that yielded a bar of iron, every furnace that melted glass or lead, all of it was drawing from a finite account that was slowly being drained. The signs of strain were everywhere. Roofs were built with smaller timbers, windows grew narrower, iron reinforcements became sparser, and walls thickened to compensate. Architects designed less ambitiously, not because they lacked vision, but because the landscape around them could no longer supply the fuel and metal to realize the grandest plans. The margins had become razor-thin, and then the world changed. In the middle of the 14th century, a wave of illness swept across Europe, a period of great hardship that historians now refer to as the Black Death. In just a few years, it reduced the population by perhaps a third or more. Entire villages stood empty, fields lay fallow, the demand for new buildings collapsed almost overnight. Cathedrals that had been under construction for decades suddenly stopped. Workers died or fled, patrons lost their incomes, and the momentum of centuries of building was broken. In one sense, this tragedy temporarily relieved the pressure on the forests. With fewer people to feed and fewer projects to supply, the demand for timber and charcoal dropped sharply. Woodlands that had been cut back began to regrow. Iron furnaces fell silent. The ecological wound that had been steadily widening began to close, not because of any wise policy, but because the human engine of consumption had stalled. But this was not a solution, it was a pause. When the survivors eventually rebuilt and the population slowly recovered, the same old patterns returned. The forests were still finite, the iron still demanded charcoal, the link between metal and trees remained unbroken. Medieval technology had reached a ceiling. The bloomery furnace could not be made much more efficient. The blast furnace, though more productive, only burned through fuel faster. The water wheel could amplify human labor, but it could not create new energy. The medieval world had no way to escape the ecological trap it had built for itself. The ambitions of its builders remained literally bounded by the reach of their woodlands. The true breakthrough, the invention that finally severed the ancient link between forests and iron, would not arrive for centuries. It came in the 18th century when English ironmasters learned to use coke, a purified form of coal, in place of charcoal. Coke burned hotter than charcoal, and more importantly, it was free of the sulfur that had ruined earlier attempts to use raw coal. Now iron could be smelted at industrial scale without consuming a single tree. The age of coal had begun, but that was a world away from the medieval imagination. For the builders of cathedrals and castles, the only fuel they had was the living forest, and that forest could not grow fast enough to match their hunger. So the great monuments we see today are not just testaments to faith and skill. They are fossils of a system that was always running on the edge of its own limits. Every soaring spire, every stained glass window, every iron hinge and lead roof tells the same quiet story. That human ambition, no matter how grand, must answer to the slow rhythm of the natural world. The medieval builders did not fail because they lacked vision. They succeeded within the boundaries of their time, and those boundaries were carved not in stone, but in wood and charcoal and the patient regrowth of forests that would take 100 years to replace what a single furnace could burn in a month. The story of their ambition is also the story of a planet that gives, but only at a pace that no amount of human will can hurry. York Minster's central tower took over 2 centuries to complete, and every phase of its construction shows the fingerprints of scarcity. Begun around 1230, the project stretched across generations of masons, bishops, and patrons, and as the decades passed, the materials available to them shifted in ways that quietly reshaped the building's form. By the time workers reached the upper stages of the tower in the late 14th and 15th centuries, the forests of northern England had been logged for centuries. Timber that once grew thick in the Vale of York had been consumed by earlier building projects, by shipbuilding, by the charcoal pits that fed local iron furnaces. The great beams needed for scaffolding and centering, the temporary wooden framework that would support the stone vault until the mortar cured, became harder and harder to find. The central tower's stone vault, a masterpiece of late medieval engineering, required an enormous amount of timber just to build. The masons had to construct a curved wooden skeleton, a centering, that held every stone in place until the arch was complete and self-supporting. That skeleton consumed oak by the wagon load, and the trees had to be straight and strong enough to bear the weight of tons of stone. As local supplies dwindled, the builders turned to timber from further afield, paying higher prices for transport and waiting longer for deliveries. These delays stretched the construction timeline, sometimes pausing work for years while the chapter gathered enough wood for the next phase. Iron, too, became a recurring challenge. The tower's vault required iron ties and reinforcing bars to lock the stonework together and resist the outward thrust of the high ceiling. But iron smelting in Yorkshire had declined as the forests around the ironworks were cut for charcoal. What iron could be produced locally grew expensive, and the chapter had to import bars from other regions, even from the continent. The cost of imported iron forced designers to use it sparingly. They placed iron only at the most critical stress points and relied more heavily on thick stone buttresses and carefully cut joints to carry the load. The result was a tower that is beautifully proportioned but built with a kind of calculated restraint. The vault is not as wide or as high as some earlier cathedrals had attempted, because the builders knew that the iron and timber required for a more daring span might simply not be available. The design decisions that shaped the central tower were not just artistic choices. They were negotiations with the landscape, with the slow regrowth of forests and the distant clang of foreign forges. By the time York Minster's tower was completed around 1472, the medieval world was already changing. The old limits of wood and charcoal had forced builders to find new ways of working, and in doing so, they had created something that still stands as a quiet monument to adaptation. The tower does not shout about its limitations. It simply exists, and its existence tells a story of patience, of working within the grain of a world that could not be hurried. Castles demanded even more from the land than cathedrals did. The great ring of fortresses that Edward I raised across Wales in the late 13th century shows this truth carved in stone. At Caernarfon and Harlech, the scale was staggering. The walls rose thick and high, built from thousands of tons of local stone, each block quarried, shaped, and hauled into place by hand. The timber needed for scaffolding soared in parallel, miles of oak beams to support masons as they laid each course, and vast wooden frames to hold the formwork for vaults and arches. A single scaffolding tower for a corner turret could consume as many trees as a small village burned in a year. And then there was the iron. Harlech's gates were not simple wooden doors. They were reinforced with heavy iron bands, studded with rivets, and hung on massive wrought iron hinges that had to support the weight of oak planks thick enough to resist a battering ram. Each hinge alone required a skilled smith days of work, heating and hammering a bar of iron until it could be bent and shaped. The portcullis, that fearsome grating that dropped to seal the entrance, was a lattice of iron bars set in a heavy timber frame, and raising it demanded chains and pulleys forged from the same metal. Every tool on site, from the mason's chisel to the carpenter's saw, was tipped or edged with iron that had been smelted in a charcoal furnace. The sheer volume of iron needed for one castle was enormous, and that iron had to come from somewhere. The smelting process was brutally inefficient, as we have seen. To produce a single ton of iron, you needed the charcoal from roughly 200 acres of woodland. A castle like Caernarfon, with its multiple gates, drawbridges, grills, and structural reinforcements, might require tens of tons of iron over the course of its construction. That equates to thousands of acres of forest, all cut, stacked, and burned to make charcoal for the furnaces. In practice, this meant that whole valleys were dedicated to a single project. The king's officers scoured the surrounding countryside for oak and beech, contracting with charcoal burners to work the woodlands on a rotating cycle. In some cases, entire forests were sold off or granted to the ironworks, leaving the hillsides bare for decades afterward. The landscape around Harlech today still shows the scars of that hunger, with open slopes where dense woodland once stood. The iron that reinforced those walls and gates came at a direct cost to the living world, and because the charcoal had to be transported to the smelters and the finished iron bars hauled to the building site, the logistical burden multiplied. Every mile added to the supply chain meant more oxen, more carts, more food and labor. The hidden cost of each iron hinge was not just the metal itself, but the slow destruction of the forest that fed the fire that made it. Edward's Welsh fortresses stand today as monuments to military power, but they are also monuments to a landscape that was fundamentally transformed by the demand for a single resource. The ambition to hold a conquered land was etched into the hills not only through stone walls but through the slow, silent retreat of the trees. Forests were not just fuel for furnaces, they were the currency of kings. A monarch who controlled vast woodlands controlled the means to build ships, forge weapons, and raise the great halls and cathedrals that projected his authority. This was not merely an economic fact. It was a geopolitical reality that shaped alliances, sparked conflicts, and determined which ambitious building projects could move forward and which would stall before the first stone was laid. In England, the system of royal forests was a tool of power as much as a conservation measure. When William the Conqueror declared large swaths of the country royal forest, he reserved for himself the right to hunt the deer and boar that roamed beneath the oaks. But the real prize was the trees themselves. The finest oaks, those tall and straight enough to become the keels of warships or the roof beams of a new cathedral, were claimed by the crown. No lord, no bishop, no abbot could fell them without a royal grant. In practice, this meant that every major construction project, from a castle on the Welsh border to a new choir for a cathedral chapter, began with a negotiation with the king. The project's patron had to petition for a license to take timber, often paying a hefty fee or offering some service in return. The king might grant the right to cut a certain number of oaks from a particular forest, but only after his own foresters had inspected the woodland and deemed the harvest sustainable. This system created a constant tension between the desire to build and the need to preserve the resource. Kings themselves were not immune to the temptation to overexploit. When Edward I needed timber for his Welsh castles, he ordered the felling of thousands of trees from royal forests across England, sometimes stripping woodlands that had been protected for generations. The local communities who depended on those forests for fuel and building material found their access curtailed or revoked. Resentment simmered. Forest law was enforced by wardens and justices who could impose heavy fines, and violations were common. Peasants caught poaching timber for a new cottage or charcoal burners who worked without a license faced penalties that could ruin a family. The forest became a site of quiet resistance as much as a source of wealth. But the power of forests extended beyond the boundaries of a single kingdom. Timber and charcoal were traded across borders, and control over this trade could shift the balance of regional power. The rich oak forests of the Baltic region, in what is now Poland and the Baltic states, supplied timber to much of northern Europe. The Hanseatic League, a powerful confederation of merchant guilds, built its wealth partly on the export of lumber and pitch from these northern forests. English shipbuilders, constantly hungry for tall, straight oaks for their hulls, looked to the Baltic when their own forests grew thin. German and Dutch merchants carried beams and planks down the rivers to ports like Danzig and Hamburg, then shipped them across the North Sea. A cathedral chapter in England or France could buy Baltic timber, but only at a price that reflected the cost of transport and the risk of sea travel. This trade in wood created dependencies. When political tensions flared between the Hanseatic cities and their neighbors, the supply of timber could be cut off, leaving building sites idle. In the late 14th century, the city of Lübeck, a Hanseatic stronghold, used its control over the timber trade as a diplomatic lever, granting favorable access to allies and restricting it to rivals. The great rebuilding of the cathedral at Lübeck itself was made possible by the city's own access to the vast forests of Mecklenburg, a resource that its competitors lacked. Similar dynamics played out in the Mediterranean. The forests of the Apennines in Italy supplied timber for the ships of Genoa and Venice, while the mountain woodlands of the Alps fed iron furnaces that produced metal for armor and construction. The Republic of Venice carefully managed its own forests in the region of Cadore, establishing a system of conservation that lasted for centuries, because the rulers understood that the city's naval power and its grand buildings depended on a steady supply of timber. The Venetian state appointed officials to oversee the woodlands, marking the best trees for shipbuilding and forbidding their use for other purposes. Violations were punished harshly. This was not altruism. It was a calculated recognition that the forest was a strategic asset, as vital as any fortress or fleet. In this world, the approval of a major building project often hinged on access to timber from a distant forest, controlled by a distant power. Patrons had to engage in what we might call resource diplomacy, negotiating trade agreements, forming alliances, and sometimes even arranging marriages to secure the rights to a particular woodland. The fact that a cathedral or castle could be built at all was as much a testament to political skill as to architectural vision. The Great Spire of Salisbury, for example, depended on timber from nearby woodlands, but the chapter had to regularly petition the crown for permission to cut trees, paying fees and offering prayers for the king's soul. When local supplies ran short, they turned to the forest of Savernake, a royal woodland held by the crown but managed by a warden who had his own interests. Every beam that was raised came with a story of negotiation, of a letter sealed and a favor called in. The forests were not a passive backdrop to medieval ambition. They were active participants in the politics of power, and the decisions made in royal courts about who could cut which trees often determined what could be built and where. The map of Europe's great monuments is therefore also a map of forests, a map of who held them, who traded them, and who had the influence to unlock their hidden wealth. The flying buttress was born from a shortage of iron. That elegant stone arch that seems to leap from the cathedral wall is not just a work of art. It is a direct response to the fact that medieval builders could not afford the metal needed to tie their soaring walls together. Without enough iron to weave a hidden skeleton through the masonry, the only way to resist the outward thrust of a high stone vault was to prop the wall from the outside with a massive stone strut. The flying buttress allowed architects to keep the interior walls thin enough for large windows, while the stone arch carried the weight down to a heavy pier set well away from the building. It was a structural solution born from scarcity, and it became one of the defining features of Gothic architecture. The very look of a medieval cathedral, its skeletal exterior, its pointed arches, its luminous interior, was shaped as much by what they did not have as by what they had. Timber roofs tell a similar story. In many early churches, builders dreamed of covering the nave with a stone vault like the Romans had done, but a stone vault is immensely heavy. It requires thick walls, massive buttressing, and a great deal of iron to tie the stones together. As the cost of charcoal for smelting rose and forest shrank, many communities found they simply could not afford the material for a full stone ceiling. The compromise was a timber roof, a wooden framework of rafters and trusses that sat above the nave, visible from inside or sometimes hidden behind a flat wooden ceiling. Timber was far lighter than stone, so it needed less iron and less massive walls. It was quicker to build, and it could be repaired or replaced without dismantling the entire structure. In many English cathedrals, the nave was originally intended to have a stone vault, but budget constraints forced a change of plan. The result is the magnificent timber ceilings we see today, like the hammer-beam roof of Westminster Hall, a masterpiece of carpentry that emerged not from a pure artistic vision, but from a practical need to work with what the land could supply. Window openings were also shaped by the same invisible hand of resource limits. In the early Middle Ages, glass was a luxury. It required vast amounts of charcoal to fire the furnaces that melted the sand and potash, and each color added to the fuel bill. As a result, windows in early Romanesque churches were small, narrow slits that let in just enough light to read by. They were not designed that way because architects preferred a dim interior. They were designed that way because glass was too expensive to waste on large openings. As the charcoal supply grew tighter and the price of glass rose with it, builders had to make careful decisions about where to place their limited glazing. Often they concentrated it at the east end, around the altar, where the light would fall on the most sacred part of the church. The rest of the building remained shadowy. Later, as trade routes opened up and glass production became more efficient, windows grew larger. But even then, the cost of lead for the frames and iron for the reinforcing bars meant that every expansion was a compromise. The great rose windows of the high Gothic cathedrals are triumphs of engineering and art, but they are also monuments to the enormous effort required to bring together the timber, metal, and fuel that made them possible. These design choices were not made in a vacuum. They were the result of a constant, quiet negotiation between what the architect dreamed and what the landscape could give. The flying buttress, the timber roof, the narrow window, these are not failures of ambition. They are adaptations, evidence of a civilization that learned to work within its limits and still create something of lasting beauty. The constraints of forests, metals, and fuel did not crush medieval creativity. They channeled it. They forced builders to find new ways to achieve height, light, and strength without unlimited resources. And the result is a style of architecture that is still admired today, not in spite of its compromises, but because of the ingenuity those compromises demanded. The scarcity of the past did not diminish the wonder of these buildings. It shaped them into something that could endure through the ages, a reminder that human brilliance often shines brightest when the world says no. And this pressure did not only reshape the form of buildings, it also drove a quieter kind of innovation, one that aimed to squeeze more work out of every acre of forest and every ton of ore. Medieval engineers and craftsmen were not passive victims of scarcity. They responded with a steady stream of small but meaningful improvements, each one born directly from the pinch of limited resources. Consider water-powered sawmills. Before these arrived, every beam and plank was cut by hand using a long pit saw, a two-person chore that was slow, exhausting, and wasteful of timber. A single sawyer team might take a full day to cut a few planks, and the uneven cut often left extra wood to be trimmed away later. But when a running stream was harnessed to turn a crank and lift a heavy saw blade up and down, the work became faster and more precise. A water-powered mill could cut through a log in a fraction of the time, and the resulting planks were straighter, requiring less finishing. That meant fewer trees needed to be felled for the same amount of usable lumber, a direct response to the shrinking forest. The same logic drove improvements in kiln design. Lime kilns, used to burn limestone into quicklime for mortar, had traditionally been simple pits lined with stone and fed with brushwood. They were inefficient, losing much of the heat and requiring frequent refueling. Over time, masons learned to build taller, more enclosed kilns with a chimney and a grate at the bottom. This design trapped the heat and allowed a steadier draft, so that the same load of wood could produce more lime. The mortar that held cathedral stones together grew stronger and more consistent, and the fuel cost per barrel of lime dropped noticeably. In a similar way, glassmakers refined their furnaces. They moved from simple open hearths to enclosed structures with a separate firebox and a working chamber, where the heat could be more carefully controlled. This allowed them to reach higher temperatures with less charcoal and to reuse the heat for multiple melts in a single firing. The cost of a stained glass window, while still high, became just a little more achievable for a cathedral chapter on a tight budget. Perhaps the most surprising innovation was the use of coal for certain industrial processes that did not involve iron. As we have seen, coal was disastrous for smelting iron because its sulfur made the metal brittle. But for burning limestone into quicklime, or for heating the vats of beer and dye in monasteries and towns, coal worked perfectly. It was abundant, often found just beneath the soil in many parts of Europe, and it burned hot. By the 13th century, lime burners in regions like the English Midlands and the Low Countries were regularly using coal instead of charcoal, sparing the woodlands for more critical uses. This was a small but meaningful shift, a way to redirect the demand away from the most stressed resource. In the mines themselves, ingenuity took a more direct form. To break through hard rock, miners used a technique called fire setting. They would build a fire against the rock face, heat it until it was glowing, then douse it with water or vinegar. The sudden thermal shock cracked the stone, making it far easier to remove with picks and wedges. This method allowed miners to follow ore veins deeper into the hillside, extracting metal that would otherwise have been left behind. It also saved timber because they no longer had to burn as much wood to heat the rock in smaller, less efficient fires. The same logic of doing more with less applied to furnace design. The bloomery furnace itself was gradually improved. Early furnaces were simple clay pits, but by the late medieval period, smiths were building taller shafts with a wider base and a more controlled air inlet. A water-powered bellows could deliver a steady blast, raising the temperature and improving the yield of iron from each load of charcoal. Some bloomeries began to use a two-stage process, first heating the ore to drive off impurities, then raising the temperature for the final smelt. This incremental refinement could boost the iron yield by 10 or 20%, a significant gain when every ton of charcoal represented acres of forest. The blast furnace, which appeared in Europe around the 12th century in Sweden and later spread to Germany and Italy, was a more radical departure. It ran continuously, producing molten iron that could be cast directly. But as we have noted, its hunger for charcoal was insatiable. For all its efficiency in producing iron, it accelerated the deforestation that it was meant to alleviate. In the end, none of these innovations broke the fundamental link between ambition and the living forest. They were adjustments, not revolutions. A water-powered sawmill saved wood, but it could not create new forests. A more efficient kiln could reduce fuel consumption by a quarter, but the demand for lime grew as building projects multiplied. Fire setting allowed miners to reach deeper ore, but the deeper they went, the more timber they needed for pit props and for the fires themselves. Every improvement merely nudged the boundary outward by a small margin. The medieval world remained trapped in a system where the energy to build and forge and melt came from the slow growth of trees, and that growth could never be hurried. The innovations born from scarcity were real and impressive, but they were also a testament to a deeper truth, that human cleverness, when faced with limits, can find ways to stretch those limits, but it cannot erase them. The forests continued to shrink, the mines grew harder to work, and the cost of metal and glass never stopped rising. The great cathedrals and castles that still stand are not only monuments to faith and power. They are also monuments to a civilization that learned to innovate at the edge of what its world could provide, and that managed for a time to build wonders within those fragile boundaries. The world of wood and charcoal had reached its limit, but change was already stirring in the shadows of the old forests, driven by a hunger that could no longer be satisfied by trees alone. The first cracks in the ancient system appeared not in the grand cathedrals but in the quiet workshops of glassmakers and ironmasters who began to experiment with a dirty, abundant fuel that had long been dismissed as useless. Coal, its sulfur had ruined iron for centuries, but glassmakers discovered that if they sealed the coal in a closed furnace and kept its fumes away from the molten glass, they could achieve the high temperatures needed without contamination. By the early 1600s, glass furnaces in England and the Low Countries were burning coal on a scale that would have shocked a medieval craftsman. The forests near those workshops began to breathe again, not because anyone had planted new trees, but because the relentless demand for charcoal had finally found an alternative. Meanwhile, new veins of iron ore were being discovered in Sweden and Russia, regions where forests still stood thick and untouched by centuries of building. Swedish iron, smelted with abundant charcoal from the vast northern woodlands, became a premium material across Europe. It was strong, consistent, and available in quantities that had been unimaginable a century earlier. The old logic that tied every ton of iron to a specific local forest began to loosen, replaced by a network of trade routes that carried metal from distant lands to the building sites of an expanding world. But the true breakthrough came in the early 1700s when English ironmaster Abraham Darby perfected the use of coke, a purified form of coal, to smelt iron. Coke burned hotter than charcoal, and crucially, it carried no sulfur. For the first time, iron could be produced on an industrial scale without consuming a single tree. The forest bottleneck that had constrained every ambitious project from cathedrals to warships was suddenly gone. The age of fossil fuels had begun. What followed was an acceleration unlike anything the world had seen. Ironworks multiplied, forests regrew in regions where charcoal burning had stripped the hills bare, and the cost of metal plummeted. Builders no longer had to calculate every bar of iron against the slow regrowth of oaks. They could design with a freedom that the medieval mind could scarcely have dreamed of, but this new freedom came with a price that was not paid in wood. Coal mining scarred the landscape in its own way, and the smoke from countless furnaces began to darken the skies over the new industrial cities. The slow, renewable rhythm of the medieval material economy had been replaced by a one-way extraction of ancient carbon. The very forces that broke the old constraints also set in motion a new kind of ecological debt, one that would accumulate for centuries. The story of how forests, metals, and fuels shaped the limits of monumental ambition did not end with the medieval cathedrals. It simply shifted to a different stage where the actors were no longer masons and charcoal burners, but steam engines and coal miners, and the monuments were no longer spires reaching for heaven, but factories and railways stretching across the earth. And yet, even as coal reshaped the world, the invisible architecture of those medieval limits never fully vanished. It lives on in every stone you touch when you walk into an old cathedral, in every beam of light falling through stained glass, in the very shape of the walls and the height of the vault. That architecture was not drawn on parchment. It was carved by the slow rhythm of forests, the stubborn chemistry of metals, and the heat of charcoal fires that burned across centuries. The next time you pass a medieval landmark, stop for a moment. Look at the roof line, the thickness of the walls, the size of the windows. Ask yourself what the landscape around that building looked like when the first stone was laid. Which forests had to fall to raise those beams? Which hillsides were stripped for the lead and iron that hold it together? Which rivers carried the stone and timber to the site? The answers are not written in guidebooks. They are etched into the structure itself, in the compromises and adaptations that turned scarcity into beauty. The builders of those monuments did not fail when they ran out of trees or fuel. They succeeded in creating something that still stands, often centuries later, because they learned to work within the grain of a world that could not be hurried. And that lesson, the quiet negotiation between human ambition and the living earth, is not confined to the Middle Ages. It repeats in every era, in every civilization, every time we push against the limits of what our resources can provide. What other boundaries have shaped the great works of history? Which materials have set the hidden ceiling on human dreams? If you have thoughts on those questions, share them in the comments. And if you want to see more stories that uncover the hidden forces behind the monuments we take for granted, consider subscribing. The next time you look at a castle or a cathedral, remember, the most important structure was never the one you can see. It was the one made of trees and ore and fire, and it held the real weight of ambition.